Today we'll be talking about 7-1 special functions and specifically about step functions. So a step function is a series of line segments, and it's also known as a piecewise function. And if you look at the parent function of a step function, specifically a greatest integer function, you'll see that the image creates these little line segments that look sort of like steps. That's where the name step function comes from. So the first type we're going to talk about is the greatest integer function. And a greatest integer function has these brackets, and they mean that it's the greatest integer not greater than the value given. So when we say not greater, that means it has to be less than. So the idea is to round down. So 6.8 would round to 6. 5.5 would round down to 5. Negative 2.3, if we think about a number line, to go less would be negative 3. And negative 4.7 would round to negative 5. Again, we want the lower number because it cannot be greater than the value. The parent function of a greatest integer looks like this. So as we put in a number or any decimal number in between, we're going to round to the integer. So you can see that it's only integers. The x values are continuous, but the y values are jumping from integer to integer. So this is the parent function, the most basic function. The graph is going to make these disjointed line segments. The domain is going to be all real numbers. We can put any value in and round it. And the range is all integers, because when we put any value in, we're going to end up with an integer as our result. So let's look at an example. If we've got f of x equals the greatest integer of x plus 2, the first column is just to do the calculations. If we think of order of operations, we're going to do what's inside the bracket first. So we're going to add the 2. 0 plus 2 is 2. And then we're going to take the greatest integer, which means we're going to round down. So that would be 2. 0.25 plus 2 is 2.25, which would round to 2. 0.5 is 2.5, which would also be 2. And then we get to 1. 1 plus 2 is 3. Rounds to 3. 1.25 plus 2 is 3.25, which would round to 3. 1.5 plus 2 is 3.5, which would still round to 3 because we're rounding down. 2 plus 2 is 4. And then 2.25 plus 2 is 4.25, which would again be 4. When we graph, we are graphing the original x value as x, and we're graphing this final value of the function as y. So this is x, and this is y, or f of x. Okay, so when we plot these points, 0, 2, so up 2, 0.25, so 1/4 of the way over is at 2. 0.5 is also at 2. When we get to 1, it jumps to 3. 1.25 or 1 1/4 is also at 3. 1 1/2 is also at 3. When we get to 2, it jumps to 4. And then 2 1/4 is also 4. So if you notice, we're forming these little line segments. Okay? Anything in between 0 and 1 is going to give me a value of 2. Anything between 1 and 2 is going to give me 3, and so forth. So I can continue these line segments across my whole graph. Okay? And then we have to think about, how do we transition from one segment to the other? When we go from 0 to 1, when we get to 1, that's where the jump is. So we put an open circle, which shows that it jumps at that point. So we're going to put an open circle. I like to call these lollipops at the end of each graph on the right-hand side, because that's where the transition moves. When you draw a greatest integer function, you should fill up the entire graph, because we can't show arrows that it continues forever, so we fill it in and then assume if the graph was bigger, it would. To write the domain, we can put any number in and round and get an integer. So we're going to say the domain is all real. And in notation, we're going to say that x, such that x is an element in the set of all real. And then our range for this particular problem, if we look, it's jumping from integer to integer to integer. So it's all integers. And that means f of x is an element in the set of all integers. Integers are z.